Hello there! It's been a long time without seeing you. So, on the previous episode of this series, we are doing parsers, which is what I don't like to be doing. So, yeah, we did a parser for the simple type lambda calculus, but there is some problems on the simple type lambda calculus. Namely, it is really verbose, and especially it is quite simple. It's simple. It does not have any form of polymorphism. Today we're going to be implementing something called parametric polymorphism. Pseudo editing Eduardo, which is about the same Eduardo as you're just watching. I forgot something really important. Don't forget to like, subscribe, enable the notification bell, follow me on Twitter, you know, the basic YouTube stuff. That was it. Sorry. Let's go back to the video. Which is effectively when the return type of a function depends on the input type. So that's parametric polymorphism. We're actually be implementing a version of the system F. System F, also known as Girard-Reynolds polymorphic lambda calculus. It's a really cool way to extend the simple type lambda calculus, but still keep the same ideas. So just to remember, the simple type lambda calculus is made of 4 typing rules. Okay, isn't it? No, it doesn't work. I need to zoom in. Okay, which are, the first one defines that every variable has a type. There is some constant types. That if a parameter has a type A, let's say, or sigma here. If a parameter has a type sigma, and if a lambda has a parameter of type sigma, and it returns an expression of type tall, so it has a type of sigma to tall. So if you have an integer and you return an integer, you have a type of int to int, so it's an arrow. And we also have applications, which is if the expression on the left has a type of sigma to tall, and the expression on the right has a type of sigma, so they match. The result expression only has a type tall. That's the idea. Essentially, if you have a function of integer and you apply an integer to integer, and you apply an integer, you get another integer. Simple as that. This effectively it's describing functions from values to values. But the word is much bigger than that. We also have, if you look on something called the lambda cube, you have 3 dimensions to extend. So first you have the simple type lambda calculus here. Then you can extend on the x, like I'm going to ignore the x-axis because it's dependent type stuff. You can extend on the y-axis, which is functions from types to values. You may imagine that parametric polymorphism fits here because you are applying a type to a function and it returns another function or like another value. So it's a function from a type to a value. And there is also the z-axis, which is when you add type operator. So you have functions from types to types. And the x-axis is going to be from values to types. It's really weird and my mind cannot understand it. So to extend on the y-axis, which is adding polymorphism, effectively there is a system for that, which is called the system F. And to extend also on the z-axis, there is system F omega, which is, well, it's an extension of system F where you have functions from types to types. Today we're going to be focusing strictly here on system F. System F has 2 additional rules. As I mentioned, the simple type lambda calculus essentially has functions and application. And the system F also adds 2 rules. This is application of types to a function, a type function. And here is how you describe a type function, from a type to a value. So I don't like this description, mostly because I don't think it's good to read. So there is this paper. I'm not sure if it is a proper paper, but it's a short introduction to system F and F omega by Pablo Nogueira. It's amazing. The blog recently is down. I don't know why, but you can use Web Archive to read it. And here he does a proper introduction. The link is going to be below because it's amazing. But if you go to this, here he tries to add, he describes the rules of the system F. Effectively, it's these two additional rules, which means he's also describing K here, which is the kind, which is something useful only for system F omega, but ignore the K. So effectively, if you have a type variable alpha and a term of type tau, you can do big lambda alpha to tau, and that's going to have a type that for all alpha, you have a tau. So for all alpha, you're going to have a type T. I'm going to use T to like A and T to make your life easier, but alpha for variables because it makes sense. So here, if you have a term of alpha to T, and you have a type sigma, you can apply this term with a type sigma, and effectively it's going to replace all the occurrences of alpha by sigma. So effectively, it's the same as a function. So all the occurrences of alpha are going to be replaced by sigma, which is the argument that you're applying. The same thing is defined here, but in a slightly different manner. Here's the simplest version. So you have a term m, where the type is a for all alpha, it returns the type sigma. So you can apply this term to a type tau, and the return of that is going to be sigma, where all the alpha are replaced by tau. That's simple. Same stuff. You get the type returned, and you just replace all of its occurrences by tau because you're applying tau. And here's the same, but he's describing the abstraction of types, where you can use the big lambda. That T symbol is a lambda, but uppercase lambda. You can use big lambda alpha that returns a term, and this term itself, so like the big lambda plus the return, has the type for all alpha, it returns T sigma. This term has the type sigma. I don't think that's gonna be intuitive for you in the first days, maybe. Like it takes some time to process it, but effectively it's much clearer when you write the code. So let's write the code. Is this code? Yeah, it is this code. So first thing that I'm going to define is extend my AST. While we could use the same AST for both type abstraction and type application, there are some problems in the future. Namely, if you are trying to do something where you don't need to explicitly define the type of the polymorphic function, for example, a Hindley-Muir type inference algorithm, you need a way to distinguish between explicit application of types and implicit application of types. So for now, we are going to be extending this. We have type abstraction, and let's move this to the side. I'm going to leave this here. Yeah. Oh, I lost it. Oh, it's here. So first we have a term, which is here. So we have a parameter, which is again just a name. We are going to keep using strings. By the way, using strings for parameters on the simple type lambda calculus leads to some problems. So ignore it. But yeah, in the future, if you find any problem with this implementation, it's quite likely to be from the fact that we're using strings on the closures. But that's not a problem for type abstraction yet. If we go to system F omega, that also becomes a problem. But let's go. Parameter, and it returns the body. It's just an expression. You can see here that because we don't need to describe the type of this type. It's just a type. There is something called a kind, which is similar to a type of a type, but it's slightly different. But here we don't have it. So, and also I need to describe a type application, which is going to be a function for an expression. And the difference here is that the argument is a type. This type is the same type as it was described here, so a T arrow. But now we also need another type, which is this. So here we are going to define T for all. It's going to be of the parameter is going to be a string. So it's slightly different. Like this is not a function. This is. Like this is a function. This is just a representation on the type system, so it's a type. And here it's kind of a function from a type to another type. And the return type should be a return type. Should be a type. Okay? So this is this part here. So the for all symbol, it's this reversed, I don't know, upside down A, big A. So here's the parameter. Alpha is going to be, for example, here, alpha. And then it returns a type. So that's the two things that we need to change on our AST. And now we need to go, first we're going to implement this on the interpreter. So let's go here. It's complaining with me because I didn't implement it. So we have a parameter and a body. And yeah, effectively we need to do the same stuff here, but we are going to copy. So on this context, we have a parameter. We also need, because there is some problems here. Yeah, I don't like it. So yeah, you're going to find, we also need to define something else. I forgot about it. Here, there is no way to reference this parameter. So we need to define a tvar of, I'm going to just use the string because you can see that this is only the parameter, is only the name of the variable. So a tvar is part of the type, right? And here we also need something else. No, I don't think so. I don't think we need to add on the context. Like we just need to infer the type of the body, declare the parameter, and declare it as body. And here it should be a T for all, where the body should be the return type. Okay, so that's the type abstraction. You can see that we are just putting the parameter here. We are not verifying, so there is a thing that you can do on this, which is have an unbounded type variable. Right now, we are going to ignore it, but that's going to be a problem in the future. So we go to type abstraction, and we also go to type application. Type application is, I don't remember. It's a function and an argument. The argument is a type though. And here it starts a big difference. There is no simple way to implement that. We actually need to do a substitution, and we don't have a type substitution yet. In the same way that we have this type equality, we need to do a type substitution. To do a type substitution, we're going to have subt type t from 2. I think 2 needs to be like this. Yeah. So we're going to replace on t from something to something. From is gonna be a string, so the parameter name, and 2 is gonna be the return. And to do it, we do match t with first t arrow. We don't do anything special for t arrow. We just do is it from type, body type, and here we do substitution. We still do the same stuff. T arrow from type equals substitution of from type from e2, and we also need to do the same for body type. So substitution from type from, so that's the first one. That's an arrow. It's effectively on the arrow we are just mapping the internal types. Tint just goes to tint. It doesn't change anything. tvar is where stuff starts to get slightly different. So here we have a name, and when the name is equal to from, we return 2. So if the name of the variable is the same as from, we just return 2 and stop. If it is not, so here tvar name, we just do tvar name to tvar name. This one is a special way to do it. Effectively, we could do an if here. So like we could essentially do this, then 2 else tvar name. But it's slightly nicer to read on this style. And then the last case it is the for all. The for all is gonna have some problems here also. So we have a parameter and the return type. But if the parameter is equal to from, so if there is a true for all with the same name, it's quite common. We use alpha for almost everything. We just return t for all from and return type. So we short circuit it. We stop going down because there is no way for an occurrence of this variable to be present inside of it. And if it is not, if it is a parameter and a return type, here we are going to also do a t for all. The parameter is the same, but the return type should be substituted. Return type from 2. Effectively, the interesting part of this function is here, like this. Because here, when we find a type variable, we're just going to replace it by the concrete type that we offered. And with this function, we can implement type application. We can go on funct. And the first thing that I need to do is infer this. So copy from there. And then we already have the argument type. So it's not needed. We need to ensure that the function type is actually a t for all in the same way that we did up there. A t for all where there is a parameter and a return type, if I recall correctly. And if that's the case, we are going to substitute the type return type. So again, so the return type of the for all is this sigma. We are substituting sigma. So sigma from alpha, which is the parameter, from pron, to tol, which is the argument. So tol here is the argument. We're replacing it by the argument. Yeah. That's the implementation of the inference algorithm. And for the interpreter algorithm, it's gonna be slightly different. I don't remember how we do it. I don't think we use, I think we just ignore it for our interpreter. So type abstraction is gonna be, I didn't thought about the interpreter. Let's go type abstraction, parameter, body. Let's do an assert false for now. And type application. If I recall correctly, we just ignore it. And type application is funct and argument. So on type abstraction, we have the abstraction, which is effectively a function. We cannot evaluate it now. I think we can go on values and add a new value just to make the life easier. So like v for all of has a context, of course, which is a value context.t. Does it have the context actually? It has anything special? I don't think so. It's not changing the context at all. Oh no, but it may be. In a body, which is an expression. And for this for all, and here we are going to ignore this type and just return v for all, where the context is the context and the body is the body. So on the application, we go and do the same stuff. The argument also doesn't matter, because remember, to execute the code, the type doesn't matter for us. We are not checking it during execution. We are checking it before. So during execution, the types needs to be right already. So that's okay. Here, if it is vint or v for all, it's a bug. Both raise a type error. And here, if it is a vint, v closure, or v native. So there is only a single case where we do anything, which is if it is a v for all context and body. We don't need to infer the type of the argument, and we can remove this. So here we just need to interpret using the context and the body. Okay, so effectively, I'm saying effectively way too much. Anyway, what is happening here is this for all is a no-op. We are just delaying it. There is no... I don't know if we could just do the execution here and ignore this. I don't know, but I'm doing it on the fancy way. I'm going to do v for all, format fprintf fmt, v for all. So yeah, that's about it, and it compiles. We cannot do it on yet. We cannot use it yet because we don't have a parser for it. Let's do a parser. The parser needs some new tokens. First, we need a big lambda, which is token u lambda, and we are also going to be using brackets, as I mentioned, because we are going to need a way to differentiate between them. So here it's going to be a new lambda, where p is equal to ident, and then there is a dot, and just an expression. So we do type abstraction, where param is equal to p, and body is equal to e. Let's see if the parser is no. The parser is okay. And during application, we do e equals another application. And here we do L bracket with a type, R bracket. So we are applying a type effectively. And here we do type abstraction of funct equals e, argument equals t. Is that right? Oh, type application, not abstraction. Yay! There is still missing the terminal one, which is gonna be quite simple. So if it is an ident here, he was using variable, but we also need to support it on terminal. So if it hits here, you can see a problem that you cannot use integer as a type. So if it is here, name, it's gonna be a tvar name. Yay, that should be enough. Let's try it. Let's try to do x. Oh, I forgot the lexer. Yeah, there is still the lexer. Else if okay, if char equals that, then lambda, else raise, and now there is an else if char equals, I don't know where I can get the lambda symbol, uppercase lambda, this one. Then it's gonna be u lambda, and there is also this, which is L bracket, and this, which is R bracket. Let's look here. Yep. So I think now it should work. Let's try A to A and see what happens. Oh, I'm not running it. Oh, yeah. You can see the type of this is a function that goes from A to A to A to A. Let's write a printer for this type because it's already getting quite messy. Let rec print. I'm going to actually use pp. I love this. So I'm going to start the old pp as ast pp. How pp, which is pp. There is no. Am I not using deriving show here? Oh, it's show type. Okay, so type pp, which is type pp type. Actually, pp stands for preprocessor. Just have a bit of fun saying it. And it has a formatter. You can write your own through the printer. And here you're going to be doing t, which is match t with. If it is a t arrow, t arrow is left associative, right? So if it is a t arrow, and the param type and the body type, and the body type and the param type is a T arrow. Okay. We are going to be doing, let me do let open formatting, printf, fprintf, fmt. Here we need to have parentheses, that's why I'm doing it. And here we do this, so pp type, param type, pp type, body type. If it is another PRO, it's not gonna have this parenthesis, body type. And here we do fprintf, fmt, of a to a, pp type, param type, pp type, body type. If it is an t-int, it's going to be fprintf, fmt of int. If it is tvar name, it's going to be fprint, fmt s, which is just a name. And if it is a t for all, it's going to be a param and a return type. I need the for all symbol. For all symbol. Yes, I don't know how to do it on my keyboard. A return type, and here we do a fprintf, where for all s, which is a parameter, dot a, I think. So here it's gonna be param, pp type, what just happened? I think my editor just glitched. Oh, I think it glitched because the special symbol. It happens. Is it running though? Oh, first is the FMT. Nice, fix it. No, it was not because of that. And here on print type, I think that's gonna be enough. Yay, you can see. So this is the inferred type. Before it was int to int. And now we can do a to a. But not only we can do a to a, because you can see that here a is not defined. So let's get things, I have it locally now. So let's define the lambda for that, which is a to this. I think that's gonna be about right. Yeah, it is. So you can see that now we have a for all alpha, we have this type. What happens if we apply a type like integer? Now you can see that it replaced every occurrence of a to that. Actually, we can describe an ID function from a to a. So this function, let's do like this. ID, which is a function where, oh, there is something missing. I forgot to I actually need also the for all four types. Token for all, where if it is for all, it's gonna be oh yeah, because I need abstraction here. I hate it. So type. I think this can be here. Can it? It's because there is no application. So maybe if it is a for all, where we need the name, right, which is the p ident, and a dot, and that's gonna be t equals type. That's gonna be a t for all, param equals p, and return type equals t. That seems to be all right. And then I need to go on my lexer and also need another character, which is for all, and get the symbol. Where's my for all symbol? Here. So now I can describe it. I can say ID has the type for all a, where a to a, like this. And we could actually just return ID to see what happens if we execute that. Let's see if it is working. It is. So you can see that ID returns ID. But actually, let's say we also accept another parameter, which is, it's gonna be before this. So I'm going to use x and x here to simplify our lives, and alpha. And this alpha, besides of ID, we are also accepting I think it's here. So here we also accept a value, which just gonna be a value of type A, and we call ID with type V. What is gonna happen here? What is wrong? Where did I mess up? So if I remove this, yeah, a type error happens. Oh yeah, right, because this is a ID has this type. First you need to apply ID to A and then ID to V, like on the image. Nope. Let's try something. Let's try to remove this and apply ID to integer. And I want to see what is going to be the returned type. Yeah, no. Okay, so yeah, that's right. It receives an ID function and it returns int to int. So if I provide an ID function by doing, I need more symbols, a of, and then it's going to be a lambda of x of type A to A, and I return, oh, of type A, and I return A. I think that matches. It doesn't. Oh, because the names. Yeah, we need to have type, okay, our equality function is not doing well. You can see here. Actually, we need something slightly different, which I don't know how to do it. So tvar, I think we can do tvar a name. I forgot to implement that. Name and tvar name prime is equal. So name equal name prime. And what was the other one? If it is a for all, right? So if it is a for all, t for all. There is some problems related here. Anyway, the idea is this can work. If we define it this as x and x, you're going to see why there is a problem. Because the problem arises from the fact that for all x to x is the same as for all a. You can see that they are the same. They are compatible. And then we need to do that equality. So I think this should work. It didn't. Why it didn't? I'm applying an argument of type ID. The type of this. Oh, because I'm not comparing, right? So I need to have t for all from and return type t for all from. I'm going to make actually from p prime return r return type. Okay, I was using actually pa from a return type a from b return type b. Okay, and if they're identical, but the problem is that they don't need to be identical. I'm going to show how to fix that in a minute also. But we could say that if param A equals param B and return type A equals return type B, actually using the equal symbol for this, so like this, equal, they work. We could say that. So you can see that now it's working. We are applying it, and by applying ID, it returns that. And if I apply 1, for example, it's going to return the integer. So this function can, you can see that this function on the left actually work with many functions. So I can do ID, and I can put not many because there is only one ID function. There is this limitation. The other cool thing about this is because we have polymorphism, we can have a function that is actually well understood. So one thing that you could not easily do on, I don't think you can ever do on the simple type lambda calculus is doing church encoding, and that's possible on system F. So like true on church encoding just returns X, and it returns Y, but this type is not possible. Like it's not possible to define on the simple type lambda calculus, at least not the generic version. Here we can do it, and even better, we can abstract over it. That's the cool thing. Abstracting over it is not going to be as useful as it may seem. But let's try. First, let's fix this. What is the problem here? If I just change the name of this variable, of this type variable, because the type is different, it's using the name from the type, you're going to see that it fails. So there is a simple trick, which is assuming if the parameters are different, what you can do is replace param A by param B on the return type of B. And you know that if they are equal, they're going to still be equal. There is some bugs on this. Please don't judge me. I'm doing the simple thing. So you can do a substitution during the equality. Here you could say return type B as A. And to do it, you can simply do substitution of return type B, where all the occurrences of parameter B are replaced by parameter A. So like this, wrong symbol. And if that's the case, if they're identical, then B as A. So we just need to verify this. To tvar param A. I think that works. Yeah, that works. So you can see that now it doesn't matter the name of this type, which was the problem before. Now it works. The last point of this video, I know it's a long video, sorry about that, is you can do abstractions on it. So for example, let's try to define a boolean type. How you can define a boolean type? A good thing is that our parser is not sensitive at all. So you can do, for example, this. You can actually define this of bool, and now you have a boolean type here. Just kidding. You need to actually inside of this, it's gonna be, because the way that we are reducing it, it's not actually completely compatible with perfect system F. There is all these sorts of tricks, but here we actually can use bool as just the name of a boolean. And if you do this, for example, you can see the type is for all booleans. And we can apply a type here, which is the type of a boolean. The type of a boolean is always going to be A to A to A to A. So that's the type of a boolean. It's going to return this value if it is true, and the other one if it is false. Isn't it applying it? So this is that. Oh, it should be for all, right? Not for all. So this is a type. There is a parenthesis. Yeah, now it's right. So we are applying our bool. And here, let's remember how church encoding works. Oh, I remember. Let's do a simple case of an if. And we're also going to apply, here we're also going to have an abstraction, if, that it's going to accept a boolean and returns the first value, which is parametric. So it's a for all. Is it a for all? Yeah, it is. So it's going to return A for, we're going to return A if it is this side and A if it is the other side. I'm not sure if even that's gonna. Okay, yeah, that's right. So here you can have the definition of the if. The return of the if is actually just A. So it accepts two A's, left and right, and it returns one of them. It's simple, but quite useful. The other trick related to this if. Why is this repeated? Oh, because there is an ID also. Okay. And the way to use it would be something like, let's say we do a value, which is also this, but it's a boolean. So we have these parameters. We have bool, first parameter, if, second parameter, v, which is the third parameter, and we are going to call if v, then 1, else 2, right? Does that type? It doesn't, because it's missing a parenthesis. Now it's missing something. What is it missing? Can I just return v? I can just return v. I can do this. Yes, I can. This. I cannot. Oh, I see why. It's because I need to apply the type. The type is going to be an integer. Now it's working. So now effectively what it's doing here is if this value v is true, then it's going to return 1. Otherwise, it's going to return 2. And we know how to define this if, which is this if accepts a boolean. But to define it, we can do like bool, which is going to be of this type. That's the type of a boolean. We need to copy the type in some places. It's not that hard. And for booleans, we are also going to accept left, which is of type. So here we do, where's my big lambda? Here. So here we do this, which is the type A. So left is A. B is right is also A. And it's gonna call bool with left and right, if I recall correctly. Left and right. Does that work? It doesn't. Why is that so? What happens if I remove this? Like this function doesn't type. So bool is an A to A to A. Oh, because I need to apply A here, right? Yep. Right. So now you can see that we are applying it, and let's pass a number. We just need to pass a boolean, I think. Wait, no. What is this being returned? Oh, it should be, okay, it should be a boolean. Yeah, that's a boolean. So how to define true? True would be something as lambda of x of a and lambda of y of a, and we return x. So like this. Oh my gosh, so many errors every time. That's actually a term. It returns an integer. Yay! So yeah, it returns an integer. It doesn't matter if we are passing true or false, but we can actually print expression. Is print expression? Oh, we can actually interpret this code. To interpret this code, I need to do let interp code, and it's gonna be parse expression of code, and then do interp context.empty. Isn't that so? Option.get. Let's try to do interp and see what happens. Oh, and then I need to print a value. How can I print a value? It's gonna be format of printf I n value dot value pp. It's wrong, and now it's yay 1. If we pass 2, so we recreated booleans. And the interesting thing is this function works for everything, and inside of this I can do any crazy logic. Let's say I'm going to pass another boolean. I'm sorry, I apologize with this, which is v prime. No, this is v1, this is v2. If v1 and v2, we can say, oh yeah, we can do an end. If v1 and v2, we do if v2, so we are also going to return an integer. We do if only v1 is true. Okay, so this fails to interpret. Why? Oh, it's missing a point. Okay, v closure, but let's apply another boolean. So both of them are false. It's going to be 3. If the first one is true and the second one is false, true. And if both of them are true, true. So I just changed this value, and now you have boolean. You have true incompleteness if you have recursion, which it's the problem of type recursion. Anyway, that was it for today. I'm sorry it took like 45 minutes. There is a lot, and I didn't make like a screenplay or something like this. But you can see that it works. And especially, this is much closer to a programming language in a way that you would like. You can extend this in many ways. You can go to the system f omega and have type constructors essentially. You can do anything here. But the important thing to understand is it's how it's built. First we had the lambda calculus, which is the untyped version of it. Then we had the simple type lambda calculus because the normal lambda calculus is not Turing complete. It's Turing complete, but it is unsound. And then we had the simple type lambda calculus, which is unsound, which is sound, but it's a pain. Like you cannot do this. You kind of can, but it's not feasible if you use bottom types and etc. And then here we have the polymorphic lambda calculus, which is the system F. And the polymorphic lambda calculus allow you to do polymorphism. You can have a function that works with many types, and that's closer to how a programming language works. Normally, the type would not be declared like this. Some languages have it. For example, in TypeScript, you can do this, essentially. So you can see that how it relates. But in many cases, we can actually infer this. As you can easily look here, A and A. So like the kind of this is definitely gonna be a base. So it would be quite simple to find the type of this. But that's the basis. I think on the next episode, I'm going to try to explain the Hindley-Milner type inference, which is much more annoying to do. System F is simple, but System F is also limited. In OCaml, we have our own subset of System F, which is, you can do actually System F omega through modules in OCaml because you have modules to modules. But it's also annoying. And yeah, you can have an idea of like these fundamentals of programming languages, how you can think about that. Thank you for your time. I hope you have a nice day. I hope like you understood something. Maybe if you read it, I think if you read this paper, it's gonna make so much more sense to you. I highly recommend. Also, give it a try on the Wikipedia page. And yeah, don't forget to like, subscribe, follow me on Twitter, comment below, enable the notification bell, you know, the social media stuff. I forgot to add one on the beginning, but don't worry, it's gonna be there. Anyway, thank you, bye. Yeah, that was it. Bye bye. You can go now.